The camera died on me. Put them back. I had decided that this braking force of 900 newtons is obviously a force, and it says that the car uniformly decelerates to a complete stop. So a complete stop tells me that my velocity is 0 at the end. And I'm looking for how far the car travels during that braking process, so I'm looking for delta x. So I know that I have v naught v looking for delta x. Well, that means I'm going to have to use, need my acceleration to use any of those first three equations we were using for Unit 1. But if I have m and force, then I can use my F equals ma. Now, F is your net force. I'm assuming right now that that is the net force on the car, the braking force. So we can plug in 9,000 equals 1,000 A, so that gives me my acceleration is 9. And then now I know V naught, I know V, I know A, and I'm looking for delta X. So nothing about time here, so that's the third equation, V squared plus V naught squared equals 2A delta X. 0 squared equals V naught squared plus 2, 9 delta X. 30 squared is 900? That's gotta be right. And 18 delta X, and then now we just divide over, and you should be getting 50. Now if you're like, wait, that's a negative 50, well, technically your force would be negative, which means your acceleration would be negative, because if you're coming in this way, your acceleration has to be in the opposite direction. But either way, negative 50 is not an answer, so we're fine. Number 9, we are looking at 3 blocks stacked on a table, and we want to know the ranking of the forces. So between block 1 and block 2, 3, 2, 2, 1, so those are 3 different forces. My first thing I check for is is there anything that should be equal that's saying they're not equal? Table in the block equals block in the table equals 1 and 2. Well, that doesn't seem likely that 1 table and block 2 equal each other, so let's look. The force between block 1 and block 2 versus the force between the table and block 1. Well, the force between the table and block 1 should be greater, because if these are all at rest, this one is holding up all 3 blocks, whereas this force between these 2 blocks is just holding up these 2 masses. So B is incorrect, because that would have to be greater than this one. Block 1 on the table is going to be greater than 2 on 1, is greater than 3 on 2. Well, okay, we'll come back to that. Table on block 1 is block 2 on block 1, and 3 equals 3 in block 2. Well, all 3 of these forces are not going to be equal. We already said for B that they would not be equal. So then now we're just going back and we are checking. Actually, A, there was something wrong. It says block 1 and the force of block 1 on block 2 is greater than the force of block 2 on block 1. We know that those 2 would have to be equal because they're a pair, 2 on 1, 1 on 2. So that one is wrong, which means C is right. So let's double check. 1 in the table would be the greatest force because it's holding up all 3 blocks. And then 2 on 1 would be the next greatest force because this force pushing up is holding up these 2 blocks. And then 3 on 2 would be the least because it's only holding up 2m. You can think about it as this one is holding up 6m, this one's holding up 3m, this one's holding up 2m. So C would be the greatest. Box 2 sits on the floor of an elevator with box 1, which is a stellar mass, on top of it, as shown in the figure. The elevator is moving downward and speeding up. So while the velocity is down because it's speeding up, that means my acceleration is also down. F1 is the magnitude of the force exerted on box 1 by box 2. F2 is the magnitude of the force exerted on box 2 by box 1. So 1 on 2, 2 on 1, these 2 have to be the same. F1 has to equal F2 because they are a pair. It doesn't matter if they're accelerating, they are a pair. So I can already cross off C and D because those 2 have to be equal to each other. And then now we're just looking for what does FG have to do with it. Is it more or less? So it tells me FG is the magnitude of the gravitational force exerted on box 1. So this is FG for box 1. So I'm going to draw the free body diagram for box 1. I have FG, and because it is accelerating down, that means that the force of box 2 on box 1 that is pointing up has to be less. So that means that FG is greater. And if you're like, wait, but you said FG is greater than F2, not F1, well, these 2 are the same, so that means FG is also greater than F1. 11, a block of mass m is accelerating with an acceleration a down the ramp whatever. We've got static and coefficient friction, which represents the friction force on the block. So we've got, it's already moving, right? So we're going to break it down. This is my mg sine, this is my mg cosine, this is my Fn, this is my friction force right here. This one is going to accelerate, so I'm going to say F net is mg sine minus force of friction. F net is just ma. Now to rearrange this, I added this one over and subtracted this one over. So they switched places, so mg sine minus ma. That is my friction force. So before I circle C, right, that is what it says. But I see that there's an option for D and C, so let's check it D. So D looks like mu Fn, so force of friction is mu Fn. We're talking about it already moving, so that would be mu K. My Fn here would just be equal to mg cosine, so let's check. Yes, either way, whether I'm rearranging my horizontal net force equation or just using mu Fn, those both give me friction force just in two different ways. 12, this one is at rest on a ramp, so I'm talking about static friction, so I can cross off D because that doesn't make sense. And we want to again find the friction force, so my free body diagram looks super similar. Only difference here is that my mg sine and my force of friction have to be balanced because again it's at rest, which means balanced forces. It's not moving, so there's no acceleration, so there's no net force, so the forces have to balance out. So the first thing I would say is my force of friction has to equal to mg sine, right? That's definitely true. And then I see that I have an option for A and B are correct, so let's look at A. A looks like mu Fn, so let's write that. Mu Fn, mu, again, my Fn is mg cosine. I am talking about not at rest, so that would be static. But the answer is actually only B. A is not correct because when we're talking about static friction, I don't have to have the friction force equal to mu Fn. It is less than or equal to. That would be like saying my desk right here has a mu Fn of 1,000, so if I lean against it, it's pushing back 1,000, even though I might only be pushing like 10 newtons. I know for sure it has to be balanced because it's not moving. Whether it has to be equal to the mu Fn, not necessarily true. I don't know that this is the point right before it moves. Any more than that, it would start to move. This could very easily be like not barely touching it at all. So it's a mu Fn, or sorry, it's a less than or equal to on the mu Fn here, so it's not necessarily equal there. What would happen to the normal force if the angle was increased? So if the angle was increased, you were getting less and less of the, what's it called, the surface pushing against that mg cosine. So the mg cosine is going to be smaller because like the part that is perpendicular is getting smaller. So you would say that your Fn would decrease here. If your angle is decreasing, so think about the smallest angle you can get is when it's flat. In this case, your Fn would actually just be equal to your mg, and that is going to be increasing then. As I get bigger and bigger angle, I get less and less Fn until it's 0. If I decrease my angle, I get more and more until it's equal to mg. The acceleration, if the angle is increased, obviously you'd have a greater mg sine, so the acceleration would increase. And then here, this would have no acceleration. You'd have to have an outside force, so your acceleration would decrease with a smaller angle. Mass m pushed at a constant speed up a ramp, so as soon as you see constant speed, I want you to think balanced forces. And we've got all these things. We're looking for friction force. So first of all, free body diagram. So my mg, this is like a ramp, by the way. So I'm going to break up my mg to my mg cosine and mg sine down the ramp. I've got Fn, and I've got this force right here. This is going to be pointing both down and to the right, because it's pushed like down at an angle like that. The part that is to the right, I'm going to call F cosine of that angle because that's the adjacent, and the part of it that was down is going to be opposite, so I'm going to call that F sine. And then lastly, we do have friction here. Because it is moving up the ramp, friction is going to oppose motion. And it told me to call the friction, oh no, it didn't. So just force of friction. And now we want to find the force of friction two ways. You could say F net equals F cos, oh wait, no, there's no F. Don't make that mistake, it's balanced, so we know that they're equal. So F cosine theta equals force of friction plus mg sine theta. And then also we can do the mu Fn route because it is moving, so it's kinetic, so they are equal. I don't have to worry as a less than. So Fn is just equal to mg cosine plus F sine. And then force of friction would be mu Fn, so mu times that, so mu mg cosine plus F sine, like this, which I think is the answer choice. Nope, it's actually not. So the other route, finding force of friction, we could use this equation, subtract over, this would be F cosine minus mg sine to get my force of friction. Either one of these are totally valid ways of finding force of friction, it's just that it was given to you this way, so your answer is D. 16, a box sits on a scale in a moving elevator. In which situation does it have the greatest reading? So the scale is just a measurement of the Fn. So this is just which one has a greater Fn, or which of the cases would it have a greater Fn? Two answers. So I'm going to draw my free body diagram. I know for the box sitting elevator, I've got Fg, and then if Fn I want it to be greatest, that means it would be accelerating up. So I'm going to cross off C and F because at a constant speed I wouldn't have an acceleration. I want to know when it would accelerate up. So moving upwards means velocity upward, so both of these have velocity upward. Both of these have velocity down, so they're moving down. Now whether it's speeding up or slowing down isn't positive or negative acceleration, isn't up or down acceleration, it's just are they V and A in the same direction or opposite. Slowing down, I want them to be opposite. So whatever my V is, it's opposite. Speeding up, I want it to be in the same direction. So same direction. And then now I just pick the two that have a upward acceleration, so that would be D and B. 17, a block is held at rest. So again, rest means balanced forces. We've got a force F exerted at an angle theta as shown. Fg is the gravitational force, Fn is the normal, F is the friction force. What do we know about the forces? So free body diagram, Fg, that's an easy one, Fg. Here, the surface is going to provide the normal force. The surface is pushing out, so this would be my Fn. This is going to try and move like down the side of the surface, so then my friction force should be pointing up. And then this force is obviously going down to the right at an angle, so that would be some component down and some component to the right. The component that is to the right looks like that would be adjacent, so F cosine, and the component that is opposite is going to be F sine, like this. And then because this is balanced, it is at rest, these are balanced, so FF equals F sine plus FG, and Fn equals F cosine. And those are probably my two answers. F cosine equals Fn, yep. And F sine plus Fg equals FF. So A and C are both correct, which is good because there's two answers. A box of mass MA is attached over an ideal pulley of box MB, which is at rest on a rough surface with a static coefficient. Which of the following represents the friction force exerted on box B? So let's look. Free body diagram. First of all, it says that it's rough, which tells me there's friction. Well, also I'm looking for it. And it says that it's staying at rest. So again, balanced forces. Free body diagrams. I've got my MAG and the tension, and these two have to be equal. For B, I've got the force of friction and the tension, and these have to be equal. If you are saying, okay, this would be MBG, and this would be Fn, and you're saying, well, friction is just mu Fn, so that would be mu MBG for the force of friction on this. Again, that is static friction. I do not know that that is the exact mu of n. I just know it's not moving. I could be pulling with a lot less than mu of n, in which case it would just be enough to balance out. So I'm not going to go that route because I don't know. When you would use that for a static example would be if it was saying like the maximum mass that will hang without moving. Because then it's like, okay, any more than that, then it starts to move, then that would be your limit. But that's not what's happening. It doesn't say anything about that, so I need to go a different route. I know that these are balanced, and I know that these are balanced. That tells me T equals MAG. And if this one, T equals force of friction, then that means MAG must equal the force of friction. So your answer was MAG, because they have to be balanced. This weight force has to equal this friction because it's not moving. We've got a block of mass M moving with constant velocity up when pushed with the force up, and we are trying to get an expression for the force up. So constant velocity tells me balanced. Here, we did one just like this a second ago, but easier because we don't have that applied force. So to do F must, and friction, sorry. Friction would be against the motion like this, so F must equal force of friction plus mg sine, and then Fn equals mg cosine here. And then now I can use mu Fn, so mu mg cosine plus mg sine, and that would be kinetic, which is why I'm allowed to just replace it with mu Fn, because I know it's equal for kinetic, so then this is my answer. Ooh, this is a good one. Block B in the figure has a mass mb and block A has mass ma. The coefficient of static friction is mu. Assume that the chord between the knot is horizontal. Find the maximum mass A can have without the system moving. So this is a case where I'm talking about static, but I would do equal mu of n because I'm saying the maximum mass. Anything more, and then it'll start to move, so that means I'm at my limit, so I can use the mu Fn, or equals mu of n for static here. I'm going to draw my free body diagram for B. So B would be MBG and Fn. I've got this, let's call this one T1 and this one T2. I've got T1 and then I've got force of friction. And then I'm going to draw just like my free body diagram for this knot so that I have T2, T1, and MAG. And then now I need to just break up my T2. I'm going to do it down here, that's fine. So MAG, T1, this T2 I'm going to break up into the left, the part, or sorry, up and to the right. The part that's to the right is adjacent, because it's touching right here, so that would be T2 cosine, and then the part that's up would be the opposite, so T2 sine. And then again, these are equal, so that means force of friction equals T1, T1 equals T2 cosine. Force of friction here we said would be mu of n because it's the maximum mass. Any more would start to move, so that's going to be mu mbg equals T1. And now I am going to substitute that in for T1 over here. So I've got mu mbg equals T2 cosine theta. And what am I trying to find? I forgot. Oh yeah, I have the second equation. This one equals, these two have to equal each other. So T2 sine theta equals MAG. I'm looking for the mass of block A, so that means this is my unknown. Now I'm going to get T2 by itself. Oh, this is a nasty question. Getting T2 by itself, substituting that in over here. So now I have mu MBG sine theta over cosine theta equals MAG. I want just MA, so I'm going to cancel out my G's. Think about it as dividing over and they cross off. And then MA is mu MB sine over cosine. I don't have that, but I do have tangent, which is okay because sine over cosine is just tangent. So this is mu MB tangent of the angle, which is B. Not A because the G canceled out. Dang, that was a long one. Alright, and 21, we are in an elevator. It's moving upwards and speeding up. So first of all, I've got FG. Moving upwards means velocity upwards. Speeding up means my acceleration's in the same direction. So that means Fn would have to be greater. So Fn is greater than the weight, or FG, so C. A block of mass M rests on a table. You apply a small force to the block, but the block does not move. Which of the following are action-reaction pairs according to Newton's third law? Force of gravity acting on the block and the normal force. The block's pull on the earth and the earth's gravitational pull on the block. The applied force on the block and the frictional force on the block. The block's push on the table and the table's push on the block. I think of Newton's third law as force of A on B equals the force of B on A. So I'm just checking which of them is just a pair of just two objects. Gravity on the block and the normal force on the block. That does not sound like two objects. Blocks pull on the earth and the earth's pull on the block. Oh look, block on earth, earth on block. That is for sure a pair. Applied force acting on the block and the frictional force on the block, not a pair. The block on the table and the table on the block, absolutely a pair. So those are my two that are guaranteed to be equal by Newton's third law. Now, which of the following forces were equal to each other? Yeah, your force of gravity is equal to my normal force here because it's at rest. The applied force is absolutely equal to the frictional force here because it's at rest. Not because of Newton's third law, though. There's a difference between these two are equal because the forces are balanced, and that is different than these two will be equal no matter what is happening because they are a pair. Okay, a crate we have here. Basically, we're doubling this angle right here, so it's pushing down more. So then, because I am pushing down more, that means I would need a greater normal force pushing up, so my new normal force would be greater than the old one. This one's from your ticket, but I liked it. We've got a force Fg like this. I know that you're moving with an acceleration east. I have a horizontal applied force like this, and a drag force, drag meaning like against, right? And then a lift force L. Now it says that I have an acceleration east. It doesn't say anything about accelerating up or down, so I'm going to assume that these two are balanced, so L equals Fg. And then my net force would be Fa minus Fd, minus because they're opposite. Fnet is just Ma equals Fa minus Fd. So that tells me B is correct, but it's a select 2. Now, because these two are equal, Fg minus L equals 0. Also, L minus Fg equals 0. That's just saying this minus this gives me a net force of 0, which is what balance means. And lastly, a block of mass M is on the surface. This one has a coefficient of friction. This is M1, by the way. So M1 has M1G and normal force and tension and friction like this. M2 is on an inclined plane, so I'm going to break up M2G cosine and M2G sine. Oops, you can't see. Normal force, this one's frictionless, thank goodness, and tension like this. This is for sure going to accelerate like this because your friction force is not going to be so big that it causes you to go the other way. Friction is always against motion. And now we're finding the accelerations. We're going to write our net force equation. Here, net force is just T minus force of friction. That was for M1A. Careful, don't call them both M's. They're different M's. T minus force of friction would just be mu Fn. Fn here would be M1G. This guy's net force is going to be M2G sine minus tension. That's M2A. I'm going to get T by itself so I can substitute in. And now I'm going to take it and substitute in. Let's move over here. I've got M2A equals M2G sine minus. Make sure you distribute that minus because we're subtracting all of this term. So minus M1A minus mu M1G. We're trying to get A, so I need to get all the A's together. So that's M1A plus M2A equals M2G. Ooh. And then now you pull out an M like this. And I'm going to divide all of that over so that now I have A by itself, and that is my A. Study hard. Make sure you go through your homeworks and old quizzes.